So in like all training session, I always ask 3 questions first, like what encourages you to learn about the pumps? I cannot read the chat box, so some of you can answer if you like what kind of drive you have, why you want to learn about the pumps, because all are chemical engineers. So pump is basically machine. So why you are so much interested? Can somebody try to answer? Hello.
From my point of view, pump is a heart of a chemical industry. Like it transfer fluids and other like our products.
Yes, perfect, wonderful answer. Any other answer?
Sir, interview purpose.
Yeah, good. That is also a perfect answer. Yes, it is required because interviewer mostly asks about the pumps. I understand. So I like this kind of honest answer. Okay, the second question is, what is that one thing you like the most interesting about the pump? You might have seen pumps, if not in the field, at least in the book, right? During the engineering. So what seems very attractive or interesting that attracts you? Nothing, right? It's always boring. Okay, then come to the third question. What is that one thing about the pump that seems boring or scary? Then I hope I will get a lot of answers. Because in second questions, I didn't get any answers. So I expect a lot of answers for this question.
Pump calculations.
Calculation, yes. Calculation is always boring, yes. Any other thing?
Cavitation.
Yes, cavitation is boring. Selection seems interesting or boring? Because we have a lot of types of pumps, right?
Interesting.
Yeah, it is interesting, yes. Okay.
Selection seems scary.
Huh? Which topic?
Selection, sir. It seems
Selection,
scary.
okay. Scary. See, if especially we are decision maker, then it is scary, you know. Like few years later, people will we will get into the history and we'll check, okay, who is the guy who selected this pump, because this is the wrong selection. If you select right pump, nobody will remember you. Okay, get down to the business. Okay, now we'll start with the basic. So why, first of all, why pump? So whether it's a human body or it's a nature of or any industry or pumping water or any chemical or refinery products, when it comes to handling or transferring fluid from one location to the other, some energy is required, right? So that there are 3 kind of forces that when fluid travels from one portion to another, there will be some kind of a losses. So we always require to raise the energy of the fluid. So when we talk about the pump, fluid is always in the form of liquid. And when we talk about the compressor, it could be in form of gas. So first thing is gravitational force. So the when there is a elevation difference, we always require pump to transfer liquid from one height to the other. So like at our home, we would have experienced when some municipality water comes at zero level, to transfer it to like a third or fourth storage building on a tank, we require some kind of a small portable pumps. Then friction force. So when fluid travels from point A to B, there is always a resistance. So to overcome against that resistance, because resistance is one kind of a force. So because of friction, it loses some amount of energy. So again to compensate that loss, we have to provide some external energy as per the Newton's law. So that is point number 2. So first is against gravitational force. Second is to compensate or to overcome friction force. And third, when the source B is at a very high pressure, and if we want to inject something, we have to give a energy higher than the source pressure. Otherwise, fluid flows from high pressure to low pressure. So if you want to make a fluid flow from A to B, then we have to inject or we have to raise the energy level of the fluid A in such a way that it is higher than the point B. So for that, we have to increase the pressure of the fluid. So in the chemical industry, you would find that when you have to inject some chemicals into some kind of reactor, you have to raise the energy level of that fluid. So these are the 3 basic reasons. You won't find any 4th reason technically. And industry, practically you will find it's a combination of 1, 2, or 3. Friction force is always there. Sometimes you will find pressure might not be there, like when you are transferring from point A to point B, there could be a possibility B is not pressurized, but just you have to overcome the elevation as well as, so when I talk about gravitation, it's about elevation, right? So you have to overcome that elevation from height, one height to the other height, and the friction loss. So these are the some of the rudimental pump and some of the very basic pumps we use in day-to-day life. All are one or the other kind of pumps. So this you can say it's a positive displacement pump. This is example of positive displacement pump. This kind of pumps you would have seen at home or agriculture. This is centrifugal. This is centrifugal. Okay, now come to the essence and technical parts. So how to define pumps? It's very simple. Different books will have a different kind of definition, but I'm not going by those complex words. So in a simple manner, if you want to define the pump is a machine which converts mechanical energy to useful hydraulic energy. It basically increases the energy level of the fluid. So when we say hydraulic energy, so it is normally a combination of flow and pressure. And mechanical energy is known to us, right? It kind of sometimes to and fro motion or rotating motion. So all this motion is called as a mechanical energy. Now, source of mechanical energy, when we require, yeah. You want to ask something? Hello? Okay. Source of mechanical energy could be electrical engine or turbine. Like, a motor is invented like around 100-150 years ago. So before that, there was no motor. So in most of the cases, the pumps were driven by either a hand or engine or turbine. But nowadays, most majority of industrial pumps or commercial application pumps are driven by electric motor, induction motor mainly. So according to the report of European Commission, pump system consumes almost 22% of electrical energy. So you just imagine world's 1/4 energy is consumed by pump. So if somebody is interested in energy saving or carbon footprint or environment, then this is a very good topic. If they learn, okay, how we can make pump system efficient by doing energy analysis and other improvements in system or pumps, then definitely this is you will find a lot of area of improvements. A selection of pumps. So when now we are diverting to purely industrial applications. So we are not talking about agriculture and domestic and other commercial applications, because we all are engineers, right? So when we have to select a pump for a given application, what all things we should have? So first, which kind of fluids we want to handle, right? Whether it's corrosive, solid contents are there. It's a dissolved solid. It's a specific what is the specific gravity of the fluid? What is the vapor pressure, viscosity? All these physical characteristics are required. Then how much amount of fluid we want to transfer, right? So that is called flow. So whether we want steady or pulsating is acceptable. What is the maximum required flow? And I hope you people are familiar with this kind of a metric unit, meter cube per hour, because you know in India and some of the Middle East country, European country, they are quite well versed with this kind of unit. But America, they use like imperial system. So in that unit of flow is gallon per minute. Now, how much height or head you want to develop through that pump? So because one is flow and the other is head, so combination of both becomes the hydraulic energy, right? So as the pump definition says, what pump does, it increase the energy level. So energy means flow and head, right? So what is the rated head we want from that pump? Then how much NPSH available and required? So we will discuss about this NPSH in the next slide. That is the important topic. Now, how reliable pump we want? Because if we want very high reliability, then we have to pay more, right? So sometimes we have to take some kind of a calculated risk or call. If very high reliability is not required, we can buy a cheap solution. What is the efficiency we are looking for? Because pump converts electrical energy to hydraulic energy. So there is, in any kind of machine, there is always some kind of losses, right? So whether we want a highly efficient pump or low efficiency is acceptable. Then initial cost, how much we want to pay, we want to invest. Then space and size, because different pump have a different shape and size, footprint. Then installation, commissioning cost, operation and maintenance cost, spare parts. So that's why pump selection is very interesting, and at the same time we have to be familiar with multidisciplinary knowledge, right? Only knowing chemical part may not take a right decision. Only knowing mechanical part cannot take the right decision. So you have to have a good combination of knowledge of different areas. Now, when we talk about the pump, normally we talk about head instead of pressure. Why? So in the simple column will explain to you. So suppose we have a 3 different column. Each column is filled up with a different kind of different kind of a process fluid. So the first column has a light hydrocarbon with specific gravity 0.8. The second column is filled up with the water. The third column is with some kind of a slurry. So in each case, if we install a pressure gauge at the bottom, would it show the same pressure or different pressure? If height of the column and cross section of the column is the same. Can anyone answer?
Different pressure, sir.
Different, right? Different or same? Same amount of liquid in all three columns. Volume is the same.
Different pressure.
Okay, why it is like that?
Because
Due
of
to different
density.
density.
Perfect, perfect. So, since though volume is the same, the pressure exerted at the bottom by the amount of liquid would be the different because of the different density, right? So it will be directly proportional to the density, right? Pressure will directly proportional to density. Now in pump, why we don't use why we not use the terminology of pressure? Because the centrifugal pumps develop the fixed head, not the fixed pressure. So suppose if we buy a pump for handling water for like 1,000 feet, and if the same pump is used to handle hydrocarbon with lower specific gravity, still the head pump developed will be the same, but pressure will be different. So pump is a fixed head machine. So it's not a fixed pressure machine. So pressure will vary with fluid to fluid. That's why we always use terminology of head instead of the pressure. Though pressure is the modified form of the head. So there is a conversion formula we can always use, like we use kg per cm square unit for pressure and meter unit for head. So if you want to convert head to pressure, conversion is very simple. We just have to multiply the pressure unit by 10 if it is water. If it is light, if it is any other fluid, then we have to multiply by 10 and divide it by the specific gravity. So if it is a light hydrocarbon, head would be more for the same pressure. If it is a heavier fluid, then head will be less for the same pressure. Is it clear? Because this is very important concept for pump.
Sir, could you please repeat for one time?
Yeah, so go back. Okay, so centrifugal pump is fixed head machine, not fixed pressure. If fluid specific gravity increase or decrease, the pressure will also vary with the specific gravity. So if we employ a pump for a certain head, and over a period of time, if specific gravity increase or decrease, accordingly, pressure will also increase or decrease, but head will remain the same. That's why we always use in the data sheet or in any discussion with vendor, we use terminology of head instead of the pressure. But head can be converted into pressure by formula. Is it clear?
Hello,
Yes,
sir.
sir.
Yes, yes.
Please take one of the example to convert the head into pressure.
Okay, so how to convert head into pressure, right?
Yes, sir. Yes, sir.
Okay, suppose we have a 2 kg per cm square pressure, right? So I want to convert that pressure into head. So for water, straight away it is a 20-meter head. 2 into 10. Assume the unit of pressure is kg per cm square, okay, not bar. So 2 into 10, so 20 meter of water column is equal to 2 kg pressure. It's very easy to remember thumb rule, right? 20 meter means 2 kg. Now, if 20 meter column is of a hydrocarbon instead of water, then obviously hydrocarbon is lightweight, right? So pressure would be less. So how much less? So instead, in that case, suppose or in other words, I will say head will be more. Suppose this is a 20 meter. So pressure will be 2 kg. Is it clear? For water, 20 meter is equal to 2 kg. Okay. Suppose if this hydrocarbon height is 20 meter, so here pressure would be less or more?
Yes, sir.
Less, right? How much less? In the same proportion of specific gravity, right? So 20 into 20 into 0.8, 20 multiplied by 0.8, right? Divided by 10. So you can write down the formula if any confusion. Pressure is equal to 10 multiplied by head divided by specific gravity. Pressure is equal to head multiplied by 10. Sorry. Head is equal to pressure multiplied by 10 divided by specific gravity. So I will give an example. Please calculate. So I want you to do some practice. If fluid is a slurry, specific gravity 1.4, and pressure is 2 kg. What is the head?
Huh? 14.3, sir.
14.3.
14.3, right?
Yes, sir.
Perfect. For the same pressure, we consider 2 kg pressure, right? For the same pressure, if fluid specific gravity is 0.9, then what would be the head?
$22.3 meters.
Okay. So now you understood, right? For light hydrocarbon, head would be more, right? Because it's light. So you can see the difference, right? For the same pressure, how head will vary, right? For heavier fluid and lighter fluid. Moving to the next. So now we have like numerous pumping technology available in the market. So to simplify, we can classify the technology into 2 types. One is a centrifugal pump and one is the positive displacement pump. So by the name itself, you can have some kind of indication what kind of mechanism is there in that pump. So in centrifugal, the fluid enters at the impeller eye. So this disc is called as an impeller, spinning at very high speed. So when fluid enters at that eye, the high velocity of the impeller transfer that centrifugal force on the fluid. So fluid will also spins at very high velocity. So velocity means it's a kinetic energy, right? So it's a mechanical subject. So if you have a confusion, it's okay. So you don't have to go that deep. But it's in short, it increases the energy level of the fluid, process fluid. When that process fluid gets collected into this volute casing, you know, this at impeller tip velocity is very high. So when it collects it here, you can see here the area is small, right, on top at 12 o'clock position. 3 o'clock position, it is increasing. So it is increasing. So this annular shape, the area is gradually increasing, right? Area or volume, you can say, right? So what happens when fluid? I'm sure you would have studied the fluid mechanics in chemical engineering, because I think that is a common subject. So as per the continuity or Bernoulli equations, when fluid travels from a low, like the bigger area, you can apply A1 V1 is equal to A2 V2. So fluid velocity will reduce, fluid will get slowed down, and the pressure will increase. So velocity will decrease, pressure will increase. So at the outlet, you will see the combination of pressure and flow. Now, according to the size of the impeller and the annulus profile, you will find different combination of flow and head. The pump manufacturer decides and design those components in such a way it produce different combination so they can cater the market requirement. So that is about centrifugal pump. In positive displacement pump, it is very easy and simple to understand. As the name suggests, it displaces some kind of a volume, right? Fixed volume. So whether it's a reciprocating or it's a rotary, it always traps some fixed volume and push that in every stroke. So you can see it captures some volume, fixed volume, and this motion will transfer this fluid to an outlet. So inlet, outlet, here inlet and outlet. So this is very simple phenomena, and since the fixed volume is trapped, the flow is always constant for any positive displacement pump, but here flow and pressure keep varying. So we will try to understand in detail in the next slide. So when any centrifugal pump develops like different flow, different head. So OEM accordingly develops some kind of a performance curve, and they publish it for purchaser, because if you have some kind of indicative flow and head, the purchaser or user can make a decision. Okay, this is for a certain flow and certain head. So this pump model is suitable to me. So this is called a performance curve. So in performance curve, y-axis you always find the head, and x-axis is always a flow. So flow versus head curve is called as a pump performance curve. So sometimes these kind of curves are produced by OEM based on their test result, or sometimes they produce based on some kind of empirical calculations or CFD or some kind of a theoretical calculation, and they load all this data into some kind of software. So whenever some requirements comes from the vendor or user, they put input condition into their software, and that will give some possible solution. So we have a varieties of
Nidhi? Nidhi? Nidhi?
to face many positive displacement pump in the industry. So now coming to the next topic, something interesting to know: why centrifugal pumps have dominated the industry. Why 7 to 8 out of 10 pumps are centrifugal pumps. So if you learn about centrifugal pumps, I think you can handle 80% of things when it comes to pump. Is anyone know the answer? You can guess. Why 7 or 8 out of 10 pumps are centrifugal pump? I want to have some kind of brainstorm session so you can remember the discussion, because if I keep delivering all the technical stuff, you will just listen and you will forget actually.
It consumes less power and it requires less area, like a small size.
Yeah, so but it's a 50% true. Conversely, it consumes high power actually. Still, it has a dominance in the market. It's not efficient pump, centrifugal pump.
It is suitable for
Yes.
most type of fluids.
Hello.
It is suitable for most type of fluid.
Yeah, this is perfect answer. So it caters a majority of industrial requirements. So you can develop varieties of flow.
Sir, we can increase the amount of flow rate. In reciprocating pump, we have the volume concised.
Yes, this is good answer, because sometimes in industry, time to time, flow requirement keep changing. So if we buy a pump for a certain flow over a period of time, if it increase or decrease, then the positive displacement cannot do that function, right? So that's why we require centrifugal pumps. Any other answer?
Due to its flow rate.
Yes, different flow rate, right?
Yes, sir. Because positive displacement pump have fluctuating flow rate, and centrifugal pump has a regular flow rate.
Yes, this is good answer. So flow, you can say flow is steady actually. In a positive displacement, there is always fluctuation or pulsation. So this is good answer. Yes. With the technology. So in centrifugal pump, when it is about centrifugal pump, you can see it's a simple design, because we have a construction wise, we have like spinning disc. Shaft is supported by bearings to contain the fluid within the casing. There is a mechanical seal. That's all. That is centrifugal pump. But in positive displacement pump, there are a lot of components. Centrifugal pump is a wide operating range. Like a pump is designed for pump at 40, 30, 60, like that. Smooth and easy operating, steady flow. Highly reliable, even have high speeds. A centrifugal pump you can find in the industry that goes up to 20,000 RPM, and positive displacement even running at 1,000 RPM is a risk. So positive displacement pumps are always very slow moving pumps. Easy maintenance, since fewer components, we can maintain it easily. Smaller footprints. The vibration wise also, the vibration has a direct relation with the reliability. If pump is vibrating at a very high amplitude, then you can always expect low reliability, right? So required for the same amount of hydraulic output is the low, small. For positive displacement pump is all about like constant flow. Sometimes dosing or that kind of application requires a very accurate amount of fluid transfer. So suppose if they want like a 0.5 meter cube per hour in a 1 minute, then that amount should not vary much. Then centrifugal pump cannot perform that kind of job. So we require positive displacement pump. It's cheaper, it's efficient, efficiency is very high. Positive displacement pump, you can find efficiency in the range of like 80-90%. That is quite normal. Centrifugal pump efficiency you can find as low as like 20%, and up to maximum you can say like 80%, 20 to 80%, depending on the flow and head. And normally it is employed for very high pressure and low flow application. When it comes to high flow, it's always centrifugal pump. So in industry, majority of applications requires very high flow. That's why you can find centrifugal pump. And the second reason is that refinery, petrochemical, and those industry cannot afford downtime of the equipment. So they can compromise with the efficiency. That's why majority of pumps in critical application is always centrifugal pump. Though positive displacement can perform that duty, but nobody will take a risk of having positive displacement pump. Is it clear? Okay. It's a mistake or a deliberate? So when we see a lot of different kind of pump, don't get confused.
Hello?
Yeah.
Sir, can you explain the applications of the centrifugal pump and positive displacement pump?
See, application is like numerous application, but you just have to look at the basic functionality. So when you have like a very high flow, you want wide operating range, you want highly reliable pump, then it's centrifugal pumps. When your requirement is very like constant flow, like each stroke you want constant without much tolerance, right? And you want highly efficient pump. Or sometimes the product is a very like highly viscous. So those products centrifugal pump cannot handle actually. I missed that part, sorry. Because each centrifugal pump, if it operates any highly viscous fluid, there will be a tremendous amount of losses because it runs at very high speed. So centrifugal pump cannot handle viscous fluid efficiently, whereas positive displacement pump, as the viscosity increase, it becomes more and more efficient. So that is the advantage of positive displacement pump over centrifugal pump when it comes to viscous fluid.
Okay, sir. Okay.
Thank you. So sometimes we think, okay, there are like if we keep classifying the pump, it could be 50, 100, and keep increasing, right? But we don't have to memorize all this silly stuff. Just we have to try to understand the basic. So being a chemical engineer, no need to go deep into that mechanical parts, but try to understand the basic principle. Like rice is the basic ingredients. You can make many things from there, right? Here also in this kind of block, you can make a different kind of toys. So similarly, mechanical engineer use some of the basic component and develop many different kind of pumps, but basic ingredients or basic components, elements, principle remains the same. So similar analogy you can apply for the centrifugal pump. So in centrifugal pump, when you see a lot of different kind of pumps, don't get overwhelmed or confused. Basic is the same actually. As we discussed, fluid enters at impeller eye, it spins at very high velocity. Whatever fluid collected into casing, that develops that velocity into the head or pressure. So when I say velocity, so velocity, flow, and kinetic energy, all three can be used as a synonymous. So don't get confused when sometimes I will use velocity, sometimes flow, sometimes kinetic energy. All three are very similar things. Velocity, flow, and kinetic energy. So when I use head and pressure, those are also similar things. So in centrifugal pumps, initially impeller converts, impeller increases the velocity or kinetic energy. And what casing does, it slow down the liquid and it converts velocity into pressure or velocity into head. That is the basic function of impeller and casing. Is it clear? So just we have to understand the basic things. So each pump will have casing, each pump will have impeller. Okay? So principle will remain the same. Principle will not change. Based on the geometry, based on the NPSH, based on the radial loading, axial loading, and other things, pump manufacturer keep on inventing new things. And that's how API 610 classify the pump into, I would say, total 18 different categories. So this OH2 pump, overhung pump, is the very basic pumps available in the industry for at least 70 to 80 years. So this is the basic pump model. We will see in detail in the next slide. And you know, some industry develop the same pump in a vertical design. Then you know, one company called Sundyne, they develop pump with very high speed. Just install a gearbox, step up gearbox in between, just to increase the speed of the machine. Then when for a very high flow, you know, radial load is very high on the rotor. So somebody thought to have a impeller in between and both the end special kind of bearings. So that is called between bearing kind of pump. So in between bearing, there are 5 different kinds of pump according to the loading. Then when there is an NPSH issue, somebody thought instead of installing pump, let's make some kind of pit and install pump at a good NPSH. That's principle. Very So as we know, more than 70% centrifugal pumps are OH2 types. In industry, as we discussed, like 70% pumps are all kind of pumps, right? Among that centrifugal pump, you will find 70% are OH2 type of pumps. Majority are OH2 types. You will find inline pump, horizontal pumps, different types of impeller, open, closed. You will find different stage of impeller, 1 stage, 2 stage. When stages are, it is called multi-stage pump. So, each impeller if any application which requires very high pressure, then one impeller cannot meet that requirement. So few additional impellers are required to be placed in series. So that is called multi-stage pump. The different standards are marked. So API is there. API you will find API 610 is market. Available between bearings are available. Vertical pumps, horizontal pumps. And mechanical seal, those are also available in the market. Then when sealers pump, so those that technology is not new, but for some people they are not familiar, so they feel it's a new technology, but that technology is available in the market for the last 70-80 years. So sealers pump is also technology wherein you can eliminate mechanical seal and seal API plants. So again, do not try to memorize everything, try to understand it, see it, visualize it, think about it, ask yourself many questions, challenge your logic and wisdom, be ready to get confused. Is it okay? Are you confused or not? Hello? Hope I have not confused you by dumping a lot of information.
Yes, sir.
Okay.
Hello, sir.
Going to next. Yes, yes. What is the difference between mechanical seal and stuffing box?
Mechanical. So so next slide I will show you pump. So you can get the answer. You want to see stuffing box, right? Can you see this? Hello?
Yes, sir. Yes, sir.
Okay. So this is basically OH2 kind of pumps. So you will find this type of construction is widely used in any kind of industries. So this is impeller. This is shaft. So when there is a shaft, rotating shaft, it requires some kind of support, right? Support means bearing. So you'll find one bearing here, one bearing here, right? This impeller spins at this two is the impeller, one is casing. So impeller spins at very high velocity. So whatever fluid enters at impeller I, this is called impeller I. Entrance point is I, okay? So across this impeller vane or blade, the velocity will increase, right? And at outlet, it will get collected into this casing, rotating casing, and from that it delivers to a discharge point. So the rear side of the impeller, back side of the impeller will also have that fluid, right? And that fluid again is expected to have a high pressure. And sometimes, you know, fluid is corrosive, abrasive, it could be a lethal, it could be a toxic, any kind of fluid is expected, right? So it is very important, it is very essential to contain that product within this pump or within this casing. And that's why mechanical seal technology is developed. So this is called stuffing box. Stuffing box is the part of the casing wherein we install mechanical seal. It's one kind of a housing for mechanical seal, you know. So here there will be a mechanical seal. So it will contain the process fluid within this pump. Because you know, if mechanical seal fails, this high pressure, high temperature, or corrosive, toxic kind of fluid, chemical will go into the atmosphere, as well as it will go into the bearing, and it will fail the complete pump. That's why mechanical seal is required, and mechanical seal is a very important part, because you know, majority of pumps issues are on account of mechanical seals.
What is the meaning of OH2?
OH means overhang pump. So this is good. Pumps wherein we have a bearing on one side, impeller on the other side. So you know, impeller is overhang, right? You can see it's cantilever. So impeller is on one side and support is on other side. So it is called overhang. So we have like 6 different kind of overhang pump in APA 610. So OH2 is the classification. So initially, you know, OH1 was the basic pump. In that, the casing was supported by the frame. Then, you know, if it is supported here by frame, at high temperature, you always find some kind of a thermal expansion. So because you know, when this part expand, the shaft center line will not remain this straight, right? So to avoid that, of late this kind of design is supported at center instead of the foot. So that center mounted overhang kind of pumps is called as a OH2 pump. So it's a center line mounted overhang pump. OH2. So now the next topic is so this is important part for chemical engineer actually. This is a pump. So you can see impeller. This yellowish part is a wear ring. You know, when fluid enters into the impeller, here at outlet it will have a high pressure, right? So if there is a no protection or no sealing, then the high pressure fluid again will go back to suction side. So this kind of a low clearance will protect the pump from excessive recirculation. Still there will be some amount of recirculation. This is mechanical seal. This is bearing. This complete part is called bearing box, bearing housing. This is how centrifugal pump works. So this is a impeller. So this will spin. So at the periphery there will be high velocity. So this high velocity. When it slowly travels from 12 position to 9 o'clock and then 6 o'clock, you know, area gradually increases. So as area increases, velocity reduces, and velocity will convert into the pressure. So this is the basic principle of centrifugal pump. So you can find closed impeller, open impeller pumps depending on the process condition. Okay, now the pump is not only about pump, but pump is all about pumping system. Because when customer complains sometimes, or pump is not performing or pump is have a reliability issue, first thing we look at is pumping system. So in pumping system, we have a pump
मैं अंदर से 1.8 किलोमीटर
suction vessel, discharge source, suction source, discharge source, suction piping. So in piping we will have a one suction valve, isolation valve, strainer is very important component. Then we will have a eccentric reducer, and eccentric expander, recirculation line. This is called recirculation line. Control valve and isolation valve. So this pumping system consists of all these components. So if pump has some issue, or in order to design a proper pump, we have to understand its environment or a pumping system. So when we, as a chemical engineer or process engineer, responsibility is to develop some kind of a data sheet, right? Because if you have if suppose in your plant, if you have a requirement of one pump in a running plant, or during the project stage, if you have a requirement of a multiple pumps, so your project team will ask you, give me a data sheet, so I can approach to a vendor for the procurement action. So it is the process engineers KRA to develop a data sheet for the pump. So how they develop? So first thing is they need to have a information of fluid, right? For which fluid they are supposed to buy a pump, right? Fluid, then flow. Okay, once they understand, we have to transfer this ABC fluid at this much flow from location A to location B. So flow is known to them, and according to the flow, first thing they will do is, like, from flow they can make out the piping size, right? Once flow is known, they will do some kind of a they will compare different kind of options, like pipe size can be ranging from like 1 inch to like 8 inch, 10 inch, 12 inch, 16 inches, depending on the requirement of the flow. Different kind of sizes are available, right? So if they select a very big size of pipe, friction loss will be less, but piping cost would be very high. If they select very small piping, it's very cheap, right? But friction would be very high. So some kind of optimization is they have to do some kind of optimization of the piping size. So once they do, and so thumb rule says some like see like in between 1 to 2 meter per second flow is good for a normal application. But if it is a slurry, then it should not be very slow, it should not be very fast. So if it is a fast, then it will erode the pipe. If it is slow, then it will get settled in some location. So once the pipe size or velocity is decided, each piping system will have some kind of a friction loss. So when we say piping system, it doesn't mean pipe. It means pipe. It means valves, fittings, elbows, suction strainer, reducer, expander, control valve, isolation valve, everything. Everything put together, it becomes a piping system. So it's a process engineer's job to identify the location, calculate the friction loss across the piping, across this suction piping, across this discharge piping, and height, what is the elevation difference between the suction source and discharge source. What is the pressure of this suction source, whether it is at atmospheric pressure or it is a pressurized vessel. So once process engineer do all this calculation. They can prepare a nice data sheet. In that they can figure out that okay, my requirement is for a certain amount of flow.
Nidhi? Nidhi? Nidhi?
They will figure out action pressure at case B X. What is the differential pressure? So pump
Heat जियो नहीं बहुत दिख रहा है।
manufacturers first information ask will you push pressure you want to pump minus X we are looking for. So, process is by how much pump they want at discharge. Something that is called differential pressure, or you can say PD minus PS is the P discharge minus P suction is equal to P differential pressure. So pump design is done based on the differential pressure and flow. So whole calculation is to arrive at a differential pressure required for that pump. Is it clear? Hello?
Yes, sir.
Yes, sir.
Yeah.
Yes, sir.
Sir, why eccentric reducer are used in suction nozzle? Why not concentric?
Okay, so you know any fluid, you will also find some in rare case it concentric,
Hi.
but it is always eccentric, because you know if it is concentric then the in the conical section on top portion there is a possible of some vapor or gas trap. So it is always advisable to keep that portion as a flat
नहीं कुछ अच्छा लिखा हुआ।
to avoid gas or air trap.
कंपनी नहीं आ रही वैसे TCS ही IT से
Okay, thank you, sir.
Okay, thank you. So once process engineer do the calculation of friction loss and fixed loss, so I will use two words. You will not find this terminology in books, but fixed loss means elevation and pressure is fixed loss. You know, it is not going to change, right, with the flow. So like in commerce, you know fixed cost and variable cost. Here also it's the same principle applicable actually. You know, fixed head and variable head. So variable head means when we calculate the friction loss, the only problem is that calculation is dependent on the velocity of the fluid. So velocity or flow. So suppose you do the calculation for a 30 meter cube per hour flow, right? Your friction head loss is suppose 20 meter, right? Now with the same piping, if you are transferring a fluid at the velocity of 40 meter cube per hour, higher flow, then you know that friction head loss of 20 meter would increase. because
Respect
if you see this formula, the friction head laws,
लोग जानते हैं पूरा
this
market
formula
में
will be the most important formula for process engineer.
बैंक भी सही है
Because
वैसे तो।
through, but nowadays you will have a sophisticated method, Excel sheet and software, so you might not use it. But I always
companies जो work from home
insist you to do calculation with this formula initially.
पर अभी
Then
most
you
of the culture ऐसे ही
keep
हो रहा
on
है।
using
Trend हो
Excel
रहा है।
sheet and other
लेकिन
software,
अपनी वही
but
चीज़ है ना,
you learn the
surety नहीं रख सकती।
conventional method to calculate the friction loss.
Surety
So you know
थोड़ा सा
friction loss,
थोड़ा
here
experience
friction
हो
loss,
जाओ ना,
and
तो
here you
इंसान
can
को
see V square. So it's a velocity. So the friction loss is in square proportion of velocity. So
नहीं आगे को नहीं करना फिर।
you know the friction loss will not remain the constant.
Marketing
So
जाओ
you are doing the calculation at certain
करनी
velocity.
sales ही है।
Now if it can be increased, it can be decreased. Accordingly, friction loss will also increase or decrease, right? So it is necessary to develop some kind of a graphical representation, right? To understand how will be the total like entire pump system curve. So fixed head is in y-axis, right? So height will remain the same, right? So suction source and discharge source will remain the same. So height is the same. If it is pressurized also, the pressure is also, we can assume it remains the same, right? Now, this is a variable because of velocity, right? You can see the parabolic shape because this is a parabola equation. You can say.
कॉलेज टू कॉलेज वही सेम रोड पे अलग
So this is a parabolic shape.
वही चीज़ है। और मुझे
So
भोपाल
this is
में
a system
पढ़ने
curve.
में मुझे पैसे का भी ज़्यादा नहीं है यार, भोपाल में भी खर्चा नहीं है।
Now, once you have defined the system curve, your job is over. Then pump manufacturers OEM job starts. They will have a multiple selections, multiple options for the required flow and head. So they will also have a performance curve. So this is a pump performance curve. This is a system performance curve. So intersection between the pump performance curve and system performance curve is the point where pump is expected to operate. Now, when system designer or process engineer
ऐसा हम लोग
calculate this
50 to 60,000
variable
बहुत अच्छा है
friction loss, one important component in the system is a control valve, you know, a control valve. So here they have considered, suppose control valve is in open condition, closed condition, 50% open, whatever condition they have considered, right? So
गली में लोकल में आ रहा है ना
system engineer should have some operating margin, right?
पब्लिक ऐसे चढ़
So that's why control valve is there. So they can manipulate on system curve by closing or opening the valve. And when they manipulate, so when they close, let's assume if valve is in this condition, valve is 80% open, 20% closed. So as they increase the closing, if valve close, it will develop more friction loss, or in opening condition it will develop more friction loss. Can somebody answer?
ठीक है सही बात है
In which condition friction loss would be more? Would be higher.
मैंने देखा यार, मैं घर से 8 बजे ना निकल जाती थी, लोकेशन पे पहुंचते मुझे पौने 10 बजते थे, और सोच इतने ही टाइम मुझे लौटने का,
इन ओपन कंडीशन
वैसे वो स्ट्रगल अलग।
Closed condition or open?
ये पब्लिक की लाइफ है तो फिर पार्टी
Open condition.
कुछ नहीं है, मतलब वो करेंगे
Friction loss would be higher in open condition.
इंसान फिर कर ही इसलिए रहा है कि हफ्ते में एक दिन ये सब करे।
No. So friction loss will be higher in closed condition. So as you just imagine, if valve is 100% closed, fluid cannot pass, right? Because of tremendous amount of friction and heat generation. If valve is fully 100% open, there is very like it's kind of least resistance path. fluid will travel easily, right? So more and more amount of fluid will pass, right? So here flow and here head. So this is pump performance curve. If there is no resistance in system, more fluid will pass, right? So pump will travel somewhere here, right? Pump will operate somewhere here. If you keep throttling valve, you are generating more and more friction. So what will happen? Pump will start giving low flow. Pump will start operating at lower flow. That's how. At one point of time, if you close the valve, no flow. So that is called shut off head. Here you have closed the valve. So this is how pump operating point will travel with the different system curve or different closing or opening of the control valve. Is it clear?
Symbiosis वगैरह
नहीं यार symbiosis तो
Please repeat the
बालाजी
concept of
वाला
it.
Okay. So when process engineer design the system curve, one of the key component is a control valve. So according to opening or closing percentage, the friction loss will significantly vary. So when valve is in fully open condition, pump will have a least resistance in the discharge or downstream. So more flow will travel through that pump, right? Because no resistance, right?
बोला ना
So as you keep closing or keep throttling the valve,
एग्जाम्स हो गए आज
it
जेट का
will
पेपर है बट मैंने नहीं दिया
give a more resistance.
जेट लास्ट पेपर है
So as the resistance increases,
बट तो मैंने सोचा कि
increases, it will flow will gradually reduce. And at one point of time, when you close the valve, pump will run with no flow. You will not see any real flow through that pump, and that condition is called shut off head. So that is the maximum head can be developed through that pump. Is it clear?
पर वही था कि यार प्रिपरेशन नहीं करिए कुछ भी अच्छा
Yes,
तो
sir.
चाहिए यार तो फिर तब भी मैंने सोच के
See, whether you are troubleshooting or you are designing a system, this is the basic concept, and you have to always remember this concept.
नहीं
Actually.
रिटर्न मिल जाए तो मेरे लिए काफी है।
Now,
Sir, I have a doubt.
yeah.
Could you please share the previous slide? Sir, in that condition, where is the...
This slide or
No, sir, graph. System curve.
next? Yeah, this slide, right?
Yes, sir. You said the control valve has significance in system
मुझे ना पहले बहुत लगता था कि
system head curve.
Right.
Sir, in that case, when 100% is open,
फिर उसके बाद
the flow rate has to be maximum, sir.
उठा रहे थे
Could you please show that on the graph?
क्राइटेरिया नहीं थी बस randomly
Suppose here we just assume this position is, I don't know, 70-80%, whatever opening, right? But as we increase the opening, it keeps traveling to on right side. After certain point, it cannot, because you know you cannot make the head loss zero, right? You can make flow zero, right?
तब इन सबके साथ दिक्कत हुई फिर
If you close the valve, flow can be this x-axis is flow, y-axis is head, right? So even if you open the control valve fully by 100%, still there will be some loss, right? And not only about control valve, but piping and other things will lead to some kind of losses, right? And there is always fixed losses, right, in the system. So you can reduce as minimum as possible, but you cannot make it zero. So it may go on right hand side up to some certain extent, but no, it cannot go here, right? Theoretically, if there is a zero loss, it can go. Are you getting my point? You know that is possible. How I will tell you. In discharge, if you disconnect everything in discharge plane, you just allow free flow, so it will be like intersection with Y point, because there is no friction, right?
तो हमें ये एडवांटेज भी हो गया था कि हमारी अटेंडेंस
Is it clear to you?
डाबर पहली बार आई
Yes, sir, clear.
है कि बच्चों को ऐसा अपने यहाँ से अच्छा माहौल दिखे तब जाके वो प्लेसमेंट और बाकी चीजों के लिए आएंगे, तो हमें बहुत पहले कर देते थे।
Okay.
बहुत है।
Now I want to start discussing about the
मैं घर चली गई थी।
most scary topic, that is cavitation in NPSH. So for that, I want to know one thing from you.
इस बार भी लाइव प्रोजेक्ट के लिए डावर
Water boils.
randomly
Sorry, it's not R but it. Water boils at 100 degrees C. So is it absolute truth or a subjective truth?
मतलब जो भी
Subjective truth, sir.
डाबर के प्रोडक्ट्स
Why?
नहीं सेल कर रहे थे, तो उनको आइडेंटिफाई
Starts boiling at 100 degrees, sir.
रिसर्च और कोल्ड कॉलिंग टाइप से ही समझ लो।
No, this statement is incorrect. Actually, water boils at or starts boiling at 100 degrees C. Okay, you just take it that way. Water starts boil at 100 degrees C. Then in that case, is it correct?
टारगेट नहीं दिया था उन्होंने कुछ भी हमें।
No, sir, it is depend on the atmospheric pressure.
हम लोग इतनी मक्कारी करते हैं,
Perfect technical answer.
लड़कियों ना सेल्स
And it is the one atmosphere at 100 degrees Celsius.
2 घंटे में
Right. So if I say water
और उसके बाद 2
starts boils at 100 degrees C at atmospheric pressure, then it is absolute truth, right?
मैं खुद भी ऐसे इतिहास में गई हूँ।
Water starts boil at 100 degrees C at atmospheric pressure, right?
कि मैं 2 करा देता हूँ फिर आप जाओ।
Is it correct?
अगर फोन भी आएगा तो मैं बोल दूंगा कि हाँ वो तो साफ है।
So is my next statement, second statement, absolute truth? Hello.
Please repeat.
ये बेचारे कॉलेज में पढ़ रहे होते थे।
Water starts boil at 100 degrees C at atmospheric pressure. Is it absolute truth now?
Absolute truth.
Perfect.
Yes, sir.
I hope you understand. So if you understand this phenomena, it is very easy for us to understand cavitation.
एडवांटेज तो होता है।
Okay, what is cavitation? So as we have seen in the previous slide, how impeller increase the energy level of the fluid, right? So you know, when normally impeller doesn't suck, but since impeller creates some kind of a negative pressure zone here, fluid will get pushed to this, because you know fluid always flow from high pressure to low pressure, right? That is the basic principle. So if negative pressure is created here, then whatever fluid is at this point will get sucked, will get pushed, I would say to this location. So how pressure transition happens within the pump, that we will try to understand first. So we have a certain suction pressure, right? So as it flows towards the suction nozzle, due to friction loss, there is always some loss, right? So pressure will decrease. From there, you can relate with this. So from this up to this point, very negligible loss, right? I would say. From here, there will be a loss because of the entrance loss. So in pump, there will be a like entrance loss. So fluid will, and you know, as the velocity increases, pressure will drop. So when velocity increase, pressure will drop. When velocity decrease, pressure will increase. So here you can say it's a sharp drop. Can you see sharp drop from here to here? Because you know velocity increases, right? From that point again here. So when it goes to this casing area, you can see pressure. The velocity is converted into the pressure. So discharge pressure you will see. So this is a differential pressure developed by this pump, right? Suction we have given X, discharge is Y. So Y minus X is the pressure developed by the pump, right? That's why pump is there, right? We required differential pressure, so pump is employed there. So Y minus X. But in between this kind of things are happening actually. Now pump can always handle the liquid. Pump cannot handle vapor, pump cannot handle gas. So when at this point, if there is a gas, vapor, any compressible form, and there will be some issue. So first we will try to understand what kind of issues it could be. So just imagine here there is a low suction. So how vapor is generated? So product can be in three form, right? Solid, liquid, and gas or vapor, right? So how product transition into the vapor form from the liquid? In which condition any fluid gets converted into vapor from liquid? Can somebody try to answer? Why liquid doesn't remain in liquid form always? It's a chemical subject, right? You people know better than me, I think.
रियल एस्टेट में तो सोचना 20,000 दे रहे थे वो लोग स्टाइपेंड अभी तक सबसे ज्यादा आया उसका।
Hello.
Please repeat, sir.
Huh?
Please repeat question.
So my question is why any liquid doesn't remain in liquid form always? Why sometimes in some scenario it is converted into vapor?
Vapor pressure
Depend on pressure and temperature condition.
Perfect, temperature and vapor, right? Perfect. Sorry, temperature and pressure. That is perfect answer. So if temperature increase, it will convert into vapor. If pressure drops, it will converts into vapor, right? So there are two things: pressure decrease or temperature increase. Is right? Understood, right? This thing. So in water example, so in the previous slide, when we discuss water boils at 100 degrees C at atmospheric pressure, but we can make water boil at 70 C, right? It is possible, right?
Yes, sir.
In other words, I will say vapor pressure of water is vapor pressure of water is 0 bar at 100 degrees C. Is it okay? Because you know water starts boil at 100 degree means water starts getting vaporized. It's inception, but it starts getting vaporized at 100 degrees C at atmospheric pressure. So if somebody asks what is the vapor pressure, then it is a atmospheric pressure, right? At 100 degrees C. So both are boiling point and vapor pressure are relevant, right? So we don't want product to get vaporized, right? We want to keep product into a liquid phase or liquid state. So that is our ultimate idea. So here, what happens? This low pressure zone is created everywhere. Low pressure, and sometimes due to friction, it generates heat. So we have two issues simultaneously. Pressure is increasing, pressure is decreasing and temperature is increasing. So that is pushing liquid to convert into vapor. So when this at somewhere here, when this liquid converts into the vapor, because this is suppose vapor pressure, right? So when pressure falls below that vapor pressure, it will convert into the bubble form or vapor form. And at certain point, again, it gets a sufficient amount of energy to convert from vapor to liquid. So initially it converts from liquid to vapor due to low pressure. When it got some amount of pressure, and again, you know, vapor can convert into liquid. So when this vapor converts into the liquid, there is some kind of a microjet effect or some kind of shock waves. So that if that kind of things happening within the fluid stream, it's okay. You won't find any major issue. There will be some fluctuation only in pressure, but if the same phenomena happens close to the metallic surface, mainly on impeller, then there will be some kind of, you can say, pitting marks or damage to the impeller. So first liquid will convert into vapor, and then vapor bubbles will get implode when that get sufficient amount of energy to convert from vapor to liquid. So that is what is cavitation. So when the vapor bubble burst, implode, at impeller wall, there will be some kind of a damage to the mechanical component. So it's not like that cavitation always lead to material damage. Sometimes you will find a low intensity cavitation. It is happening there, but it won't resulted into some kind of damage. But still it is a cavitation. Is it clear?
Yes.
So it looks scary or interesting. I want to make it interesting instead of scary. So cavitation doesn't mean damage always. If it is a severe cavitation, then you will find damage, okay? So there is no damage, it doesn't mean cavitation is not happening. Still there could be a cavitation. Okay, next. Now how, so to understand and to eliminate the cavitation within the pump, the most important technical term is the net positive suction head, because in this slide, our ultimate aim is to keep liquidity into the liquid form, right? Liquid phase. At any point of time, if liquid converts into the vapor, then there will be issue, right? So if we make a foolproof system, process system in that, liquid never converts, or we always make sure liquid always remains in the liquid form, then this cavitation will not happen, right? So in order to make liquid into liquid form, or in order to make sure we are supplying liquid to the pump, we have to make sure the suction pressure is always higher than the vapor pressure, right? So this indicator, NPSH, is the indicator that will help us to understand the supplied fluid to the pump is in liquid form or it could be in vapor form, because we want to keep it in liquid form. So in the field, to get indication of an NPSH is very easy, you know. On suction, you always find a pressure gauge. So our idea is to keep liquid in liquid form, right? So as long as suction pressure is higher than the vapor pressure, the fluid will remain in liquid form. If vapor pressure is more than the suction pressure, the fluid will convert into the vapor. Is it clear? Or it's confusing? So our idea is to keep suction pressure higher or vapor pressure higher? What is our ultimate goal?
Suction pressure.
Okay. So never get confused. Suction pressure should always be higher, right? Keep suction pressure higher, keep suction pressure higher, keep suction pressure higher, right? So cavitation will not happen. As long as suction pressure is high, cavitation won't happen. So you want higher suction pressure, not higher vapor pressure, okay? So you want suction to win, or you want vapor to win. So if you want suction to win, then suction should be higher, right? Simple. So just calculate the difference between suction and vapor and convert it into the head. So you will get NPSH available. Is it difficult? Very simple, right? If suction pressure is 2 kg, vapor pressure is 1 kg, then it is, and if it is water, then our NPSH available is 10 meter. It's very simple, right? Okay, now this is very simple, but the condition 2 is a bit complex, and that is the job of process engineer. So when during the design stage, when they do the system design, they have to communicate this NPSH available to manufacturer or OEM, pump OEM. So because pump manufacturer will ask them, what is NPSH available in your system? So in that case, they have to do some gas estimation work. So gas and estimation combinedly in industry use as a guesstimation, So they have to do some guesstimation work because system is not there, right? So they have to just calculate based on the formulas and based on the anticipated condition, right? And so here they have to calculate. They have to calculate like here the in short they want to figure out what is the expected suction pressure or head at the suction flange. So for that, the first thing is the if there is a pressurized source, then what is the suction pressure? So HS is a suction pressure. They have to convert into head because here they have to convert everything into common currency, right? Because we are talking about head, not pressure, right? So whatever pressure, whatever things we have to convert into the head, and then we can do some kind of a algebraic sum, right? So if this tank has a 1 kg suction pressure, right? We can convert into the head. Then this height, why it is plus or minus, why it is not plus, why it is not minus, why it is plus minus?
According to pump suction or lifting.
Right. So if it is if elevation is in positive side on top, so suction vessel is on top of a pump, then it is a positive. If it is on bottom side, then it is a kind of a lift. So it will be a negative, right? Then friction loss. So this pipe, fittings, valves, strainer. So what is the friction loss? Then this is velocity head. You can neglect this because this will not be a significant. So you will not find sometimes velocity head in this formula. Sometimes you will find, so don't get confused. It is a negligible. That's why sometimes people don't consider it. And most important is a vapor pressure, right? So because our entire calculation is to fight with this demon, right? So vapor pressure. So whatever vapor pressure is available to you, because it's a process engineer's expertise to get that vapor pressure, because there are certain methods are available, or they will have a standard vapor pressure curve for the product. So once they have this detail, like if they are handling some hydrocarbons, so for suppose butane, there will be some kind of a vapor pressure curve. So they can get that value, but you remember this vapor pressure value is always on the absolute pressure because it's not practical. They get it through some theory, right? So theory always yield something in absolute, not gauge pressure. So other things, this will be, you will have in a gauge, but this value you will have in absolute. So always correct it to a gauge pressure, or you correct it in absolute. So all the units will become the same, right? So that's how you can finally come to a NPSH available. And this value, you have to pass it on to a manufacturer. Now, manufacturer, what they do, they have a many different design, and each impeller have a different kind of a like construction and all these things. So that determines that will tell you how much NPSH that impeller has required or that pump has required. So suppose you have a NPSH available at site condition 10 meter. Now if you communicate that 10 meter to manufacturer say, okay, I have 5 different pump. One pump my one pump required as NPSH of like 8, one pump 5, one pump 11. So okay, 11 you keep it aside. So I don't want that. So 8 and 5 you can discuss on 8 and 5, right? So whatever value pump manufacturer gives as a NPSH required, we don't have to do anything on that. So it's a purely based on some kind of empirical or theoretical calculation from pump manufacturer. We can't do anything on it. It's a inherent characteristic of the impeller. So you got NPSH R and NPSH A. Is it clear to you? So I quickly rushed through the data sheet and performance curve. We have 15 minutes. So this is a API data sheet. So process engineer's job is to complete the input condition. So during the project stage, you will be given this kind of an editable format. So you have to fill it up by doing all the analysis, calculations, research. So this is a basic naming of the equipment and tag number, everything, right? Then here you can mention the liquid characteristic. What is it rated, what is expected. This is the operating condition you are looking for. NPSH at datum, pumping temperature, flow, right? This is what you are looking for, right? Because you have figured it out through all the calculation. This is the site condition and other things, whether it's indoor, outdoor, what kind of electric area classification you are looking for, right? Based on the type of industry. This is the information manufacturer will provide based on the input condition. So they will feed all your data into their software, and they will find some solution, some options, some selections. So if they have multiple selection, they will fill in this data sheet for you to compare a different selection, or you will get this kind of data sheet from 3 or 4 manufacturers. Then you can do a better evaluation, right? Comparison, efficiency, and how is the operating range, and how is the power requirement. All these things you can compare. So next stage is construction and all these things. I think project people or mechanical people, rotating equipment engineer will support you filling this information out. It's I think not your duty, but it's a project engineer's job to do this. But first, figuring out the operating flow, pressure, and NPSH available is your main duty as a process engineer.
Hello, sir.
Yes.
Can you explain NPSH with example?
So with example, suppose if you have a suction pressure of 1 kg, right? At pump suction, okay? Now, if you are handling a water at ambient temperature, so in that case, water vapor pressure at ambient temperature is almost like 0. So what will be your NPSH available? Because you have a suction pressure, suction pressure is 1 kg, right? And vapor pressure is like 0. So 0 we are considering just absolute, right? So in that case, we have like 10 kg of, we can say, so 10 kg of positive pressure we already have, right? Sorry, 10 meter of positive pressure, because 1 kg means equivalent to 10 meter, right? Because we are considering water. So we have 10 meter, but you know, absolute the vapor pressure is in form of absolute pressure. So we have to convert this gauge pressure into absolute. So 1 kg gauge is equal to approximate 2 kg absolute, you know, because we have to add 1 kg, right? Atmospheric pressure.
Okay.
Are you getting this point? So 1 kg gauge is equal to 2 kg absolute. Is it clear to you, to all of you? When you're reading any gauge pressure, it is always approximately 1 kg higher than the absolute, subject to pump is installed at sea level. Is it clear? Hello?
Yes, sir.
Okay. So here, our pump suction is 1 kg gauge. So 2 kg absolute. So 2 kg absolute means, you know the formula to convert from pressure to head, right? So 2 multiplied by 10 divided by 1, right? Water specific gravity is 1. So we have 20 meter of NPSH available in that case, right? But this is in the condition where we already have a suction pressure. But during the plant design, or when you are buying a new pump, you won't have a suction pressure reading, right? So in that case, your job is to calculate NPSH available to provide to the pump manufacturer. So what you do, so you just make some kind of a guess and estimation work, right? Like this is your pump location, where is your tank location, what all piping components would be expected in between, like length of piping, fittings, elbow, right? And then strainer. So you calculate friction loss, you calculate elevation, you have a vapor pressure, and what you do, you just consider all the component like friction. So which all components will be negative, which all components will be positive, that you have to try to understand. So friction loss is always negative, right? Vapor pressure is always negative. Pressure in the system is always positive. Elevation, if it is suction is on top of pump, it is positive. If it is on lower elevation, if it is a lift condition, it is a negative. So based on that, you have to do the algebraic sum of all these 4 components: pressure, head, friction loss, and vapor pressure. Again, I repeat, pressure, if it is atmospheric pressure, you don't have to do anything. Just you convert 0 gauge into absolute. So it will be a 10 meter of head. So 10 meter plus friction loss. Sorry, friction loss will be minus, vapor loss will be minus. And if you have elevation of suppose 50 meter, you add 50 meter. If it is a lift, 30 meter, then 30 will be a minus. Do you get my point or no? Again, confusing. So if you want to understand which for which component, which element sign will be positive or negative, just try to remember or it worsen the situation, it deteriorate the situation. So if I have more pressure on suction, it is good or bad for NPSH calculation? Hello? In suction vessel, if I have a more pressure, it's good or bad? Can someone try to answer? It's good, right?
Yes, sir. Good. It is good.
High pressure is good, right? Okay, so it for pressure sign will be positive, right? Okay, having more height on positive side means at higher elevation it's good or bad? Suppose I have 40 meter, 50 meter height, static height. It's good, right? It improves the situation, right? Condition. So that will be positive. If I have a lift, suppose vessel is at lower elevation than the pump, it's bad, right? So its signature will be, the sign will be negative. Vapor pressure is always negative, right? And friction loss is good or bad? It improves the NPSH or it makes situation worsen, or it reduce the NPSH, because friction loss is loss, right? We are losing something. We are losing the energy. We are losing the pressure. It means always minus. Okay.
Yes, sir.
So pressure component always positive. Head component could be a positive, could be a negative, depending on the location of the suction tank. Friction loss always negative. Vapor pressure always negative. So do that algebraic sum and you will get the final value. That is your NPSH available. So that's why this formula, you can see. So this is the formula, right? So, okay, I will give example. Suppose we have a, now if you have a notebook and pen, please try to calculate. So at suction source, pressure kg gauge pressure, pressure 30 meter height, friction loss of entire system is a 25 meter, and the fluid vapor pressure is 2 kg, then what is the NPSH available? Please try to calculate. So first we will convert all pressure into absolute, then we'll convert pressure into head, and then we will have a four different head. We will have suction pressure head, friction loss head, vapor pressure head, and static head. And we'll do the summation. Did anyone get the answer? So I will try to calculate here. What is the suction pressure at source?
2 kg.
Huh? 3 kg. Right?
2 kg.
So we can consider this is a 2 kg. So can we consider in absolute 3 kg, right? So 3 kg if we converts, we cannot do the conversion. Why? You know, because we don't have specific gravity, right? So assume specific gravity is 0.8. Okay. So if we have a specific gravity of 0.8, then what would be the head? So is equal to 3 multiplied by 10 divided by 0.8, right? So this is the head we have with suction pressure, right? Now what is the static head? Elevation?
30 meter.
30, right?
Yes, sir.
30. Okay. So this is 30, right? This is, let's say, pressure head. What is the friction loss?
25 meter.
25. What is the vapor pressure?
2 kg.
2 kg. Already in absolute. So we just have to convert into head, right? It is already absolute. So what we will do, 2 multiply by 10 divided by, what is the specific gravity we assume? 0.8, right?
Yes, sir.
0.8. This is the vapor. So we got all 4 head, right? Now head will be positive. This HS will be positive. This will be positive. This we have to subtract, and this we have to subtract, right? So is equal to this plus elevation minus friction minus vapor pressure, right? Our NPSH available is 17.5. Is it clear?
Okay, sir. Got it, sir.
So you will get some examples from internet or somewhere. You try to do practice. It seems very easy, but you know, if you don't do practice now, then you will again forget it, right? You will find lift. Suppose instead of this Z is lift, and we just have to instead of this as a positive sign, we make it negative sign, right? Minus minus 42. It's not good, right? So whatever fluid that suction will automatically get